Hey everybody, Dave Lindbergh in Hong Kong with another episode of THD Podcast. Today we have a company named Greenwaves joining us from France, is where they're headquartered, and they've got an edge processor doing a lot of things on low latency and using some interesting methods to process some things on the edge. So we're going to find out about that. But before we forget, let's give a shout out to our sponsor, the IoT Association, the Audio and Loudspeaker Technology International, a great networking company for people building speakers and systems and promoting components, all that kind of thing. It's a great organization to get involved with, so we encourage people to do that. Now let's get into it. So Simon joining us from Japan. How are you doing this afternoon, Simon?
Good, thanks, Dave. I have to admit I didn't do my homework, so I have no idea what Greenwaves is at the moment. So starting as a blank sheet, this will be interesting.
That's kind of the purpose of this podcast, is to allow people to get an introductory presentation to cool audio tech. So Martin Croome, VP of Marketing from Greenwaves. How are you doing this morning for you?
Great. Thanks, David. Good morning.
All right. And are you in the UK or are you in France?
I'm actually in France, just close to Grenoble in France, which is where we're based.
Okay, very good. So yeah, Greenwaves, I mean, I previewed the technology a little bit. It does look like an edge device. I hope I didn't butcher that. But perhaps, how about now is a good time to get into a presentation to tell everybody what it's about.
Great, thanks, David. So I'll go into a little bit about Greenwaves and about our processor GAP9. So Greenwaves is a 7-year-old fabless semiconductor startup. We're based out in Grenoble in France. We have about 40 full-time staff, about 10 consultants, so about 50 in total. And really our focus is to sell, design and sell high-performance processors, but for energy-constrained devices. And that very much plays into hearable type devices. Okay. We also have some offices in Bologna, Italy, and we have a sales office in Shanghai, China. But we also have sales agents around the world. Okay. Our Bologna, Italy office is actually just next to the University of Bologna, and we have a very strong relationship with a couple of universities, the University of Bologna, and also with ETH Zurich, which is a university in Switzerland. And they jointly have a program called PULP, which stands for Parallel Ultra Low Power. And we have a very strong affinity with that program, which is actually producing a lot of open source designs. And so we have a very strong open source background to what we're doing, which is quite unique in the semiconductor industry. Okay. Our first product, GAP8, has been in production since 2020, was one of the first commercially available processors using something called RISC-V, which is a new instruction set architecture. You can think of it as a bit like the ARM instruction set architecture or the Intel x86 instruction set architecture. It's a new one. And what defines it is that it is open source as well. It's in fact an open spec because an ISA is just a piece of paper. And it was also one of the first commercially available microcontrollers that started to look at how to do artificial intelligence, neural networks in small, very low power MCUs. Okay. Our next generation product is called GAP9. We have silicon back. We're starting to ship this to customers at the moment, and we expect to be in production in 2022 in Q3. And that's the product that I'm really going to talk about because that's the product that really expands us into the hearables market.
Okay.
Is that also this RISC-V based processor?
Yeah, absolutely. It's based on RISC-V. It's really an evolution of the architecture. It's in kind of two ways. One, it's on a more advanced process from a semiconductor perspective. And secondly, there's a lot of architectural improvements. And there's also some really new stuff, particularly around audio and low latency audio.
Does that RISC-V spec or this instruction set, does that actually govern the physical chip design?
No, not at all. No, RISC-V is just basically, well, you could say that it can actually cause a change in the way that you do the design because but it's really just what are the instructions that the processor will understand? What's the format of those instructions? And then one thing which is unique about RISC-V is that RISC-V allows you to actually, firstly, RISC-V is very modular, has lots of different kind of sets of instructions which are optional. And the spec itself explains how to kind of switch on and switch off, say what you have actually implemented of those optional specs. It goes one step further, which is you can also add your own instructions in a standardized way that the runtime platform can query and understand about the processor. And that means that you can have a very modular compiler architecture, which allows you to kind of switch on and switch off these different instruction sets. It's used now by, I think the last count I saw was that over 400 members, significant, chip producing vendor members that are signed up in RISC-V. It gets used hugely in deeply embedded designs where you don't actually even see the processor that's there. So if you wanted, pretty much now, if you need some kind of controller core inside a chip that you're making, that's not going to be exposed to a customer, you would use RISC-V. I mean, it makes total sense. So you can just take a core, and then the cores which implement that spec. There's lots of them, lots of different core designs, and a lot of them are open source as well. And the one that we use comes out of this Pulp program, and is open source. Has also actually been taken up by something called the Open Hardware Group, which is also kind of doing a lot of verification work around that core, and improving the quality of the core. And that's really the advantage of this open source stuff, is that all of these eyes go onto the same thing. It's the same thing with open source software. You get lots of different eyes looking at the same piece of software, so the quality is greatly improved. And also the second thing, which is very interesting, is that an ISA is essentially as good as the tools that are around it.
Yep.
So if there's a lot of companies using an ISA, then you start to get a lot of traction around the tools, and that makes the tools good.
Yep. Does the just because we're on top of the open source aspect of it, is there a factor that you insulated from patent wars type of problems with open source?
Well, I mean, if you think about what a semiconductor company is doing, it's always doing a certain amount of integration of different portions there. So I mean, there's always this problem of a potential lawsuit around that.
Yeah.
I mean, there's been a lot of discussion around that. I'm not sure it makes it more risky. Quite frankly, I'm not sure it increases the risk.
Okay.
So our markets generally with Gap9 are really around kind of three different subjects, which is low latency DSP, so kind of digital signal processing on signals which are sample by sample, which require extremely low latency processing. So you can think of things like ANC as being a classic thing that requires that. And then kind of general digital signal processing algorithms, so general kind of either frequency domain, time domain, digital signal processing, combined with neural network loads, and potentially also some traditional machine learning. We can support that as well, but generally that's kind of what we see. And inside products which are range from IoT type devices, so that's a very broad, IoT is a very broad statement, but it can go everything from kind of intelligent sensors, which are interpreting richer data like camera images, radar, human signals, things like that, to kind of doorbells or something of that sort, some more sort of IoT product. Then through wearables, so things like smart glasses, particularly not so much the very high data rate, kind of smart glasses with video stuff happening. But more, things which need to be more power efficient. And then hearable products. So everything from earbuds to professional audio to headsets to professional things which need to, do very deep noise suppression and all that kind of stuff. And then within that, we're doing, a number of different things which kind of combine these technologies together. So either, kind of pure NN things like, data interpretation, like scene detection, object detection, face voice ID, but then also things like transformation, things like denoising and effects and so on. And then through things which are more hybrid, like they're a mix of kind of traditional DSP or low latency DSP and NN, like perhaps having an ANC system, which is steered or adapted by a neural network. or using beamforming with neural network technology, which has been greatly explored, and then kind of pure DSP things like spatial audio, and all of these trying to run them as efficiently as possible, but also giving a large range of flexibility to the person developing these algorithms. So if I kind of like summarize GAP9 in a nutshell, it's basically a combination of these things. So it's three kind of processing tasks: real-time, streamed, autonomous time domain digital signal processing. And there we have something which we call a smart filtering unit, which is a quite unique IP developed by us that's inside the chip, which does that and does a great job of providing a large amount of flexibility in that task. Then a general digital signal processing, and there we use something that we call a cluster, and I'm going to go into a little bit more about what that is. Mixed then with highly flexible neural network processing. So there we have the cluster, which we also use, and also a neural network accelerator that we call NE16. All of this done at extra low power, so really focused on energy constrained devices. So we're not consuming watts, we're not consuming hundreds of milliwatts, we're consuming single digit milliwatts, or maybe 2 digits in milliwatts, down to tens or hundreds of microwatts, and then really flexible and really as easy to program as we can make it. Obviously, an MCU is embedded processor is always going to be a challenge to program, but we try and make the design as homogeneous as possible to make it possible to really have a fast time to being able to program the thing. And then all in a very small component that can fit into these kind of devices. So it's a 3.7 by 3.7 millimeter WLCSP package, which can be integrated into these kind of hearable devices.
Okay.
So here I'm kind of like diving into deep architectural stuff, but I'll try and keep it at quite a high level. Basically, GAP9 is kind of like a combination of two things. On the left-hand side, it's kind of like an MCU. There's a core, which we call a fabric controller. As I said, these are all RISC-V based. So we've enhanced the RISC-V ISA with a number of things very specific to our kind of workload. So that includes things like DSP type operations, so things like hardware loops, saturation, max, clipping operations, all of these kind of things. Then we include a bit manipulation engine inside each of the cores, so we can do things like bit shuffles and pop counts and so on and so forth, which is very useful for a lot of algorithms. And then we have a lightweight vector unit, which is inside each core. So that can process 8-bit or 16-bit vectors. And then finally, in GAP9, and this is an evolution versus GAP8, we include something which we call a trans-precisional floating point unit. And so this is a floating point unit that can handle 32-bit floats, but also 16-bit floats, so IEEE 16, and also bfloat 16, which is a format that's heavily used inside the neural network world because it keeps the exponent of the float 32. So the range is actually the same, more or less the same as a float 32, but obviously losing a lot of precision because you've only got 16 bits. So the mantissa is much shorter, but the exponent is maintained in terms of its range. That's then combined with a memory area with RAM and flash. What's in fact EM RAM, so it's a flash equivalent. So non-volatile equivalent, and then combined with a very smart peripheral controller that essentially can do a lot of things autonomously in terms of managing peripherals and manages DMA channels per peripheral. In fact, the peripherals almost manage their DMA channels themselves. Then we have a very rich set of interfaces, including an audio interface, in fact, 3 serial audio interfaces with up to 48 channels, total TDM channels coming in through those interfaces, with master-slave capability, lots of clocking options, and so on and so forth. And then also per audio SAI interface, we have 3 PDM in and 1 PDM out per interface. So there's a lot of audio input and output capability there. There's also, as you can see, camera interfaces, which can be integrated for external cameras as well. This peripheral controller, we call this a micro DMA because it's kind of like a programmable DMA unit, but it goes a bit further than that because it can also actually do kind of transformation of information on the fly. And one of the things that's located inside that micro DMA is what we call the smart filtering unit. So it's really close to the interfaces. So actually, the smart filtering unit can autonomously process interface to interface. So you can take something in over a PDM interface, for example, decode it, sample by sample, process it the moment the sample arrives, and send that process sample out over another PDM interface, PDM output. But also the SFU can be used to transform information as it's coming into the memory. So it can write into our L2 memory area, which is the big block you can see there. And it can also take stuff in blocks from the L2 memory area and send it out to an interface. And it also actually can process memory to memory. So it can be used as a kind of offload processor for audio time domain filtering tasks. Then on the right-hand side, we have this thing which we call the cluster. So what's the cluster? It's kind of like a calculation engine. So it actually has 9 RISC-V cores, identical to the first fabric controller core. And in fact, all of these cores are not only identical, but they have the same memory map, which means that if you can compile a function, you can run that function anywhere on any one of those cores, and it will run identically. The only difference will be the speed that it has in terms of its access to memory. And this is a real advantage in the sense of being very homogeneous. You have one compiler, you program the thing in C, you don't drop down to assembly code or difficult things like that. It's a very, very classic architecture in terms of programming it. So all of those cores have very fast access to a shared L1 memory area. So when I say very fast, that means single cycle access to that shared L1 memory. And then those cores are actually managed in terms of all of the synchronization of those cores in hardware. So when we fork a task out onto those cores, it's done in hardware. When there are synchronization primitives like barriers or things like that, it's all handled in hardware, which allows us to be very fine-grained about the things that we can parallelize on that structure. And then we combine that in with this NE16 AI accelerator. So that's really focused on accelerating things like convolutions and linear layers and matrix operations and things like that. And when it can't do something, because it's a dedicated piece of hardware, so it already always has limitations versus a processor, we can take over with the cluster. And I'm going to talk a little bit how that's a little bit different to a classic DSP architecture and what difference that makes. Then finally, all of the memory movement in terms of data in the chip is organized using these DMA blocks. There's no data caching in this chip at all. And that allows us to have an architecture where we're really ideally suited towards a streamed workload, where we know exactly what's going to be moved around in terms of sizes at compile time. All we need to do is fill different stuff in the blocks that we're moving around. And we have a number of really sophisticated software tools that allow you to manage doing that kind of work, which even to the point of actually just generating the code for you for managing all of this data movement across the architecture.
So this, just a quick question, if you don't mind just going back one slide for a second.
Yeah.
You're talking about the SFU can perform some operations on memory, so passing through the DMA channels.
Yeah.
Up to what point? I mean, what are we talking about? At what point does it become a main processor job as opposed to an SFU job?
The SFU is really optimized. Well, I'm going to talk a little bit about the SFU on the next slide, but okay. The SFU is really optimized around processing sample by sample audio filters. So think of biquads and FIRs and things like, that kind of stuff. So if your task that you want to do fits into the concept of an audio graph and a sample by sample audio graph, even with multiple different clock domains and so on and so forth managed within that graph, then the SFU is the perfect thing to do that. And because the SFU is really a peripheral, it's something which you set up with the graph that you want to execute, and then you start it and it goes on working. So when it's given samples, it will take them in and process immediately and spit out. Because it's working like that, it allows it to be very power efficient, because it's not a processor that has to load instructions or do things like that. It's optimized around this task. Very, very low latency. So down to it can process in kind of classic ANC filter structure. It can process a single sample in under 1.3 microseconds. So it's down to that, and that's essentially real time at 768 kilohertz. So it's taking in a sample, doing the physical processing on it in real time at 768 kilohertz through a quite complex audio graph.
Yeah, I see. So it's based around if you only need to deal with one number.
Yeah, it's based around if you need to deal with a stream of numbers, because there's stream of numbers. Now, if you have a block, like a block of samples that you want to process through it, you can load that block of samples into the L2 memory area. You can point the SFU at it, and it will load them in, and it will spit them out to another buffer, it will spit them out over an interface, whatever. And it will also tell you, an event, hey, I need another buffer, and so on and so forth. So it will keep running until it finishes doing that. And really, your benefit is going to be you offload the processor for doing something else. You do it at very, very low power. And then, obviously, if you're doing it interface to interface, you do it at a very, very low latency between those two interfaces.
Yep. And then in terms of memory, so the diagram shows 128 kilobytes shared memory.
Cluster, yeah.
Pardon me?
In the cluster L1 memory zone.
Yes.
So the actual RAM of the L2 is 1.5 megabytes,
I see.
which is over here.
Yeah.
And there's also 2 megabytes of the non-volatile EMRAM.
Okay, it's actually a lot of RAM.
Okay. Then we also actually have an external memory bus. Well, yeah, it seems like a lot until you start doing neural networks. And then it's sometimes not a lot. Then we have an external memory bus, which is switchable between Hyperbus, Octo, or Quad SPI, or SDIO. And in fact, in the WRCSP package, we expose one of those, but the chip, in fact, has two. So we have some other package options that we're looking at that expose the two. And that memory, any of the memory, this EMRAM or that external portion can actually be mapped into a virtual space of the L2 inside the chip memory. Buffered through the L2, so you can essentially have a kind of virtual memory system. It's a fairly rudimentary virtual memory system, but that allows you to execute pages of code in place. Inside the.
And you mentioned that everything's programmed in C. Now this is kind of more general question on the state of affairs with processing, but historically going down to assembly would make things a lot leaner and faster. So is that kind of a non-issue to the benefit of people able to easily code in C nowadays with your on the cluster side of things?
Yeah, I mean, in kind of classic processing, a compiler is probably going to do a better job than a programmer at optimizing. Until you get down to some very, very specific kernel that then, for example, I'll give you just an example of that. When we're doing kernels which are using the vectorization capabilities, vectorization is an interesting compiler problem, and there's certain instructions where the vector optimizer is probably not going to get to it. For example, we have an 8-bit 4x4 dot product. So it's 4 times 8-bit vector times a 4 times 8-bit vector. So if you think about that, that's 4 multiplications, it's 4 max basically, with an accumulation into 32 bits. So that's actually 8 ops that are happening. It's quite a deep thing for a compiler to optimize to. So we've actually implemented built-ins in GCC, so you can just use a built-in. So you still don't have to go to assembly, but you can use the built-in and the vector capability that's inside GCC to actually express that you want to use that instruction. So in that kind of case, we drop down to that. The only place where I think we actually get down to assembly code is in certain bits of certain OSs. But that's really because we're manipulating. It's like context switches and things like that. So it's really pretty deep. Otherwise, no, I think a compiler probably does a better job. Unless you're really considering a very small piece of code.
Yeah, and I think for support and commercial deployment, allowing people to use that versus finding a dinosaur that can still do assembly is a lot easier.
Yeah.
Okay.
I must admit, we still look at the assembly that's generated by the compiler to check that we're not doing something silly. So.
Right. Okay.
So I've kind of mentioned a little bit about what the SFU is. I'm going to be quite high level about it. Essentially, it's kind of a number of different resources, which are hardware resources that can be combined into an arbitrary graph. So it's actually a very general purpose device that can be used in a lot of different scenarios. Really what we designed it around was ANC, and there it delivers both excellent structural latency and excellent power consumption. And complete determinism, so it can run between two interfaces without being disturbed by anything else happening on the chip. Very good observability, so you can observe all the points in the graph. But it can be used for loads of other things, and people are already starting to explore how it can be used for things like heavy duty filtering, for sound spatialization, for effects, for things like that. And one of the interesting things is that it's dynamically reconfigurable on the fly, so you can actually have multiple graphs running in this. But also on an individual graph, you can reconfigure the coefficients without stopping the graph with a number of different strategies to do that, to avoid glitching. And that provides a very interesting idea of combining this with neural networks. So I'm going to talk a little bit about how you combine, say, a classical sample by sample filtering structure with a neural network.
Okay.
Just to explain the cluster in terms of parallelization a bit, and what's the difference between kind of a classic SIMD type approach. The cluster is lots of cores, right? But they have free running program counters, so each of the core is running on its own. And the only synchronization that's going on is handled in hardware. So we can synchronize very, very, very at a very fine grained level. What does that mean? Well, it means that when we fork something out onto all 8 cores, we can do it in under 4 cycles. When one of the cores perhaps has finished what it's doing, hits a barrier, which is kind of synchronization primitive, then 1 cycle later it's clock gated. When all of the cores hit that in that barrier group, hit that barrier, 1 cycle later they're already started up and running again. And that's really important to get the fundamental thing that we're searching for with parallelization, which is speed up. How much faster can we go? But the interesting thing is we don't use that speed to actually go faster. What we use that speed to do is reduce the clock speed of the processor, which in turn allows us to reduce the core voltage, and that gives us a quadratic benefit in energy. So we use dynamic frequency and voltage switching heavily inside the chip, so you can dynamically change the core voltages in multiple different domains. For example, when you're not using the cluster, you switch it off entirely, and it's not consuming. The other nice thing about having these free running cores is that you can have a number of different approaches to parallelization. So, for example, if you have something like a biquad filter, where essentially the next step depends on the step before. Well, it's clearly not something that you can just like split the data up and set a core to work on separated data. There we can start using kind of pipeline structures where essentially the cores have a lightweight semaphore implemented in hardware that essentially is synchronizing them, and you kind of pipe stuff through the cores. The first one handles the first sample, and then it's passed to the second core, which does something else to it, and so on and so forth. And obviously you can mix these together. So you get really powerful structures that you can bring in terms of benefit here.
Okay.
What would be the advantage of that pipelining?
So essentially, if you have something where the next step depends on the previous step, then you cannot use the divide and conquer approach to parallelizing it, right? But what you can do is you can pipeline it. So essentially, you can handle the first stage of the biquad in the first process core, the second in the second core, the third in the third core, and that will still give you a speed up because, in a sense, you're handling a pipeline of samples, right? So you need or a pipeline of blocks of samples potentially in this case, because the sample by sample processing, you've probably done it in the SFU.
And I'm curious, how what makes that faster than a single core just running these operations in sequence?
Because essentially if you were a single core, you'd be in a loop handling each stage of your biquad, right?
Yep.
Cascade. If you're in a single process, then you'll loop around, right?
Oh yeah, I got you.
Your loop is expanded onto the cores.
Yeah.
Essentially.
Yeah.
Okay.
that's very different to the classic DSP approach. And the classic DSP approach, has kind of VLIW approach where you try and let the compiler schedule parallel instructions, okay, and then put that all into one big long instruction word, which is loaded and then executes. But that assumes that the compiler can fill that instruction word, which is often not the case. So it's often the case that there's not 100% efficiency there. Whereas with the cluster, these synchronized but free running cores, it's much easier to schedule stuff onto them. And if they get desynchronized, actually there's a benefit in that. If those things get desynchronized, then probably they're going to access the memory with a different pattern, and in fact, the way that the memory architecture works tends to desynchronize them. So you get much, much better cycle power efficiency doing that. And we've done some tests. We have an implementation of the LC3 codec, which we did from the specification, and this we've implemented on the cluster. So we've parallelized it. We've done a parallel implementation of it, which we release out to our customers open source, and we've compared that with a classic DSP architecture running that LC3 codec. And we come to figures which show us using 2 times less cycles and 3 times less power per operation, giving an overall benefit of 6 times less energy running that LC3 codec inside the cluster. And then we combine that, as I said, with this NE16, tightly cooperating with it. So when there's something the NE16 can't do, the cluster does it. When something the NE16 can do, which can reduce the energy of doing the big filter operations, then we use the NE16. And then finally combining that with the smart filtering unit and its processing capability, which is a very high precision sample by sample processing capability. Again, all of this is kind of parallel processing capability that's all there. It gives you a huge amount of processing power that you can apply to the problem. That isn't something you're going to apply all the time, because otherwise you'd be draining the battery. But what it does give you is some ability to accelerate, to have some room on the accelerator pedal, so that when you have multiple simultaneous real-time things that need to be happening, and you have a kind of peak point, which is very awkward for you to manage from an engineering perspective, you have the power to be able to just power through that, essentially. And that makes the engineering of this kind of hearable product much, much easier.
Okay.
So the most interesting thing for me is what our partners do with this. So what gets done with GAP9, and we're a processor company. We're not a software company. We do a lot of software, like most processor companies, because we do a lot of tools to allow our process to be used efficiently. But really, fundamentally, we're not experts in spatial audio. We're not experts in ANC. So we reach out to partners that are, and they work with us to port their stuff onto GAP9. So we've got a number. I'm not going to go through them in great detail, but a number of partners that have been doing great things with GAP9. One, Iden Audio. They're doing work on spatial audio, so rendering real-time spatial audio using an IMU to track head movements in real time, and then re-rendering the audio in real time. So that's a kind of example of one of the things that can be done on these kind of platforms. A partner, Orasound, based out in France, they're doing a number of different things. ANC with AI-based steering of the ANC. They're also doing work on AI noise reduction, and really working on these kind of like really low power consumption signal improvement architectures. Then we have a company called Segotia. They're doing a very interesting thing using GAP9. They've already ported one element of this. This is essentially a technology where they're cross-correlating brain signals, so EEG signals, to separated audio. So you separate some speakers in audio. So obviously you do some kind of beamforming to separate those. And then they have a technique which allows them to use a neural network to figure out from your brain waves which of those separated audio signals you're actually trying to listen to. And obviously from that, then allowing you to enhance that. So this is a great example of using neural networks and a combination of neural networks and sound processing to process stuff.
That's amazing. Like the old Beatles recordings, you could find out which channel people are focusing on.
This is actually just, if you're listening to multiple speakers, you separate the speakers inside the device, and then you cross-correlate between the speaker signals and the EEG signals, and allows you to select which of those different channels you're trying to listen to more than the others, which obviously allows you to enhance and pick up that one some more.
It could be also interesting for training or people with hearing disabilities, helping them to focus, or all kinds of other attention focused mission critical type applications. That's really cool.
There's a lot of uses of that.
Yeah. Wow.
I mean, actually the spatial audio, the IDEN stuff, I think there's a huge amount of uses for that, particularly in disabled kind of applications as well. Or even, if you think about in a warehouse, someone who's doing picking in a warehouse, being able to tell them, hey, pick the parcel from, lot 42 with a direction to it. Yeah. So that it turns their head towards where they need to go to. Yeah. There's loads of ways you can think about using direction in audio to enhance the user interface, I think.
Yeah. You can see more people walking around the grocery mart asking where something is, and then their app will be telling them, and
and the sound will be coming from the right direction of where the
thing is. Localized. Very cool.
And then finally, we've got this partner, Cyberon. They have a really nice, this is a basic thing like keyword spotting, but the nice thing about their keyword spotting engine is actually that you can compose the language that it can understand just from words that are text in a database. So you can actually recompile the engine without training data of those specific words, because it's working on syllables, and it allows it to kind of build a training set, and retrain the engine quite simply to understand this new keyword set. And it has very low resource requirements. It's running at 500 microwatts, which is very reasonable for that kind of thing. Yes, okay, you can find better, but it's pretty good.
That's another big category. I know that people trying to develop their libraries with studios is an expensive and lengthy proposition to get all the accents and everything covered. So it mentions global language support here. That's a massive issue.
Yeah. So we've got evaluation boards, which are now available, that I said we're shipping out to customers. We actually do our kind of evaluation board as the kind of sandwich stack up. We have a core module, which has GAT9 on it. It has some memory, test points for testing power and things like this, in an M2 format. We don't use the M2 standard from an electrical perspective, but we just use the connector. And that makes it really easy to make a prototype board with GAT9 very quickly, your own prototype board if you need to. And then we have a kind of generic EVK board with JTAG connector and a kind of expansion plug for various different formats of things that you might want to add in. And then a really nice audio board with DACs and amps and our own kind of amp design that we've done, which is a differential digital amplifier that can actually combine, can tack on directly onto our PDM interfaces. So it's quite an interesting amp design, and that's available now and shipping out to customers.
Great.
From a development tool perspective, we have pretty complete set of development tools. So as we've mentioned, the base compiler is GCC, so you can use C, C++. And then we have, obviously a debugging and programming bridge. We actually ship as part of our SDK a full SOC simulator. So this actually simulates the entire chip, plus MFAC peripherals around it. Super powerful. It's really nice and combines with a profiler, which allows you to visualize the running of your code on the device. So you can actually see, for example, on the cluster, your code executing, so you can see the DMAs, how they're being used, the cores, how they're being used. You can drill down to actually exactly, okay, at this point, there seems to be a gap here. What's actually executing there? Which function is executing there? And you can drill down, visually into it. And GVSOC gives you about 10% error versus in terms of cycle count versus the real platform. So you're executing the real code, you're executing the real compiled code, and you can actually even do things like simulate audio interfaces and have WAV files pumped in through an audio interface and things like that. Then from neural network perspective, we have a number of tools that allow you to get from neural network environments like PyTorch, like TensorFlow, all the way down to gap code, and then a load of different examples of different networks and different network types, everything from image to sound networks, lots of different types to help you there. And then this foundational tool, which we call an autotiler, which is the kind of code generation tool for everything to do with moving data around the platform. So this is actually directly called by a lot of the what we call generators, which are libraries of different kernels for neural networks. And then we have a complete audio tool set, including a runtime that allows you to actually process audio graphs across these multiple different resources. So things like the SFU, the cluster, and even code running on the fabric controller.
Okay.
Just quickly, yeah, that term, audio graph and SFU graph. I'm not familiar with the term graph. Does that mean like a chain of events?
Yeah, exactly. It's basically just a chain of operators. I mean, we use graph a lot because it's just like it's describing a sort of set of filters that are connected together, which looks like a graph, right? Neural networks, much the same thing. You have an input, it goes into a convolutional layer, goes into a activation like a ReLU, and then another convolutional layer, and then another activation, and so on, or through different operators. And sometimes you have multiple paths through the graph. So it's essentially a computational graph. And the interesting thing is that if you think about it, audio is that really. Sometimes you want graphs that switch on and switch off, but fundamentally it's a load of graphs that you construct your audio path with. And neural networks are the same thing. And in fact, those graphs at the time where you design your application, what are they? You also know the size of things that are passing through them. And that's what allows us to exploit that and actually generate all the code for kind of passing things through these graphs at the time when you compile your program and automatically.
Yeah.
Okay.
So neural network, people will be very familiar with things like TensorFlow and PyTorch. These are the two kind of icons here. These platforms generally have some kind of export format where they can spit out a graph of their network. TensorFlow exclusively uses a thing called TensorFlow Lite. PyTorch and several others use something called ONNX, which is an open kind of format for that. And then we essentially have a tool which we call NNTool, which does everything to do with quantization, compilation, optimization of the graph, and spits out something that kind of glues onto handwritten kernels for the really significant layers, which make a big difference in terms of performance, and also spits out C code of compiled versions of smaller kernels where it's not so optimized, or it doesn't need so much optimization. And that's kind of pumped into the autotiler, which actually generates the final code. And then, with loads of examples in this. One of the big benefits about our tool set is our ability to handle lots of different types of precision. And the reason why that's important is that you obviously, as you quantize more, you get more performance and less energy used. However, obviously you have accuracy problems, but if you can do that in a flexible way where you can kind of mix different levels of quantization, you can get a much more effective solution to an audio problem. And audio is tricky. With neural networks, audio is particularly neural networks which are sitting within the audio channel, so they're actually processing something that someone's going to listen to. That's obviously much, much more challenging than processing something and coming out with some kind of decision. I'm in a bus or I'm in a cafe or something like that, where it doesn't really matter. You're not going to transform the audio for the listener. But precision becomes very, very, very important when you start transforming audio.
Mm.
And then, as I said, we have these audio tools which allow you to map, audio graphs onto onto the various different resources which are inside the processor. And that really concludes the presentation.
Okay.
Nice one. I'd like to start the talk with the comment that you're just going to keep it at a fairly high level and then go heavily into memory mapping technologies. But that's fantastic.
Yeah, no, it's all very good stuff. Very good. I think some people, I know myself, I'll watch it a couple times as I edit it later. So I always remember more after I've done that. But that was great, Martin. Any more questions from you, Simon?
No.
Okay. So everybody watching, we'll put the details how to get a hold of Greenwaves in the description below. And of course, encourage everybody to like, subscribe, and share. And so Martin, Croome, thank you so much for joining us today. We appreciate your time.
Thank you.
Okay. Bye, everybody.
Goodbye.